Okay, hi there. Today, for pre-calculus, I'm going to be covering proving identities. Before I get to proving identities, I got a couple problems here to show you, which were kind of more of the introduction to identities. So I'm going to do these first. The proving identities really has to do with when you have an equal sign, and you're proving that the two things are equal to each other. All right, so first one. If I was looking at this one and I wanted to combine these, I need to get common denominators, okay? Which means, the most basic of common denominators is when you multiply. If I had 1/5 plus 1/7, I'd multiply the left one by 7 over 7 and the right one by 5 over 5. So I'm going to multiply this one here by the 1 minus sine x over 1 minus sine x. The other one I'll multiply by the other denominator, which is 1 plus sine x. Okay, and when I multiply those together, 1 times the numerator will stay the same. But when I multiply the denominators together, that's a difference of 2 squares, which gives me 1 minus sine squared. Sine of x times sine of x is sine squared of x. This one I get 1 plus sine of x over the same denominator, right, which is my whole point. So now I can add the numerators together and keep the denominators. So I got 1 minus sine x plus 1 plus sine x all over 1 minus sine squared x, okay? And then when I look closer at the numerator, some stuff cancels out, which is great. Which is really kind of why I did that whole thing. Minus sine x plus sine x is 0. And 1 plus 1 is 2. And next I know that 1 sine squared of x plus cosine squared of x is 1. So 1, if I took that and manipulated it, I get 1. This will be cosine of x. Cosine squared of x, excuse me. So you could either say that or, 1 over cosine is secant. Oops. 1 over cosine is secant, so this could also be secant squared of x times 2. That's probably the best answer, okay? One over cosine is secant. All right, so that's the first one. Second one. A little trickier than the first one. If I want common denominators here, I should multiply this by cotangent of x over cotangent of x, since this one's already got that denominator. Okay, and when I do that, I get cotangent squared over cotangent of x minus this one I'm not changing at all. It shouldn't have a squared on it. This should just be an x. Okay, and then when I subtract these, I get cotangent squared, cotangent, not cosine, minus cosecant all over cotangent of x. Okay, next, you're going to look up you got to look up some of your formulas if you got them on your formula sheet. One of them, look for one that has cotangent squared and cosecant squared. So if I look through those formulas and I find this one over here, the 1 plus cotangent squared equals cosecant squared. If I took that and manipulated it, brought the cotangent and the cosecant to the same side and then moved the 1 to the right side of the equal sign, you'd get cotangent squared minus cosecant squared equals -1. So that numerator, in other words, is -1. So I get negative 1 over cotangent of x. And that's a dandy answer. Remember, 1 over cotangent is the same as tangent. So a better answer would be negative 1 times the tangent of x, or negative tangent x. Okay? And that would be my answer. Number 3. So this one, once again, define common denominators. There's nothing simple about that. You just multiply, the left fraction by the sine of theta. And the right one I'm going to multiply by 1 over cosine of theta times 1 over cosine of theta, then combine them, okay? So I got sine of theta, 1 plus cosine of theta by the other denominator. Cosine of theta over sine of theta. This one I'm going to multiply by 1 plus cosine of theta. And go down that road, and hopefully we can get some stuff to simplify. So numerator, sine times sine is sine squared. My denominator is going to be, I'm not going to multiply this out, the whole thing. It'll be sine of theta times 1 plus cosine of theta. Okay. This one, I get cosine of theta times plus cosine squared of theta, all over the same denominator. So if I combine them together now, I got, add the numerators together, sine squared plus cosine of theta plus cosine squared of theta, all over the same denominator. All right, so I get that. Okay, now what I'm looking for is, stuff that I can cancel out. Sine squared plus cosine squared is a biggie. All right, sine squared plus cosine squared is 1. Okay, so these two here are 1, which means my new numerator is 1 plus cosine of theta all over sine of theta times 1 plus cosine of theta. Okay, now I'm looking for anything else I can cancel. Ooh, I see there's one more thing, right? They both have 1 plus cosine of theta, which is beautiful. The whole thing cancels, which means I'm left with 1 over sine of theta, which of course the best answer for that one would be cosecant, right? Because 1 over sine is the cosecant. So that whole thing boils down to cosecant. That's pretty nice. All right. So, number 4, here's the last one of these, I think, before I get to the proving, verifying the identity. All right, so this one looks like kind of straight multiplication, right? If I multiply those together, the denominator is a difference of 2 squares, right? So like, x plus 2 times x minus 2 is x squared minus 4. The denominator is going to be 1 squared is 1, always a subtraction sign. Sine times sine is sine squared of y. My numerator, if I multiply these two things together, I get cosine squared of y times 1 plus sine of y. So I'm looking at this. Remember, cosine, there's that Pythagorean identity, sine squared plus cosine squared equals 1. Which means if I took 1 minus sine squared, if I manipulated this, 1 minus sine squared would be cosine squared. So that denominator, I can change that into cosine squared. So those cancel, which means I'm left with 1 plus sine of y. And I think that's it. That's as simple as you're going to get with that. Okay? So that's the answer. So here comes the new stuff. Verifying each identity. So this one has an equal sign. And there's a couple of simple rules with this. To verify or prove an identity, you only manipulate one side of the equation. All right, that's the big rule. And students don't often like this. They like to multiply. The golden rule of algebra says you can multiply both sides of the equation by something. But here, you're just manipulating one side, which makes it a little trickier. And here's the tip, and I remember my teachers telling me this. It's usually easier if you choose the side that's more complicated and manipulate that, okay? You don't want to start with the easier side because there's often things that you won't see, okay? Whereas if you take the harder side and try to make it into the simpler side, life's usually easier. We're kind of hardwired that way anyway for manipulating. So for simplifying. So this one, if I was looking at this one, the right side looks harder than the left side. So I'm just going to take that one and I'm going to start manipulating it and try to get it to be tangent cubed, okay? So first thing is I can pull a tangent out of this. I'm looking at that and I'm thinking, okay, I can pull a tangent out of that. Tangent of x. So if I do that, what's left? Well, I got secant squared of x minus tangent divided by tangent is 1. Okay. Now I'm looking at my formula sheet and I'm going, geez, can I make a secant squared and a 1? Is there anyone in there with a secant squared and a 1? If I look at my formula sheet, you should see this one here, right? Which means if I take that equation and I subtract 1 from both sides, I get tangent squared equals secant squared minus 1, which means this here is going to be tangent squared of x, okay? Which is beautiful because now I've got two tangents on over here and one tangent there. So if I multiply those together, I get a tangent to the third. And your last step should always be that these two things equal each other, and that's your proof, okay? You can't just write that tangent cubed equals tangent cubed with no steps, all right? You got to prove it. This is like, you know, a different kind of a proof in mathematics. You know, in geometry, you saw these two-column proofs with the statements and the conditions, and you were proving that these two triangles were congruent to each other. You know, this is the same idea. It's just a little, it's a little different with trigonometry. Okay, so next one. You know, I'm looking at this and I'm thinking, which one's harder? You know, and you could do this one probably either way, to be honest with you. I'm going to manipulate the left side. Before I do that, let's just keep in mind here that cotangent, that's the same as the cosine of x over the sine of x, right? So if I can manipulate my equation and get that, I know I've made it to the cotangent times cosine, okay? So taking the left side now, if I take this and I go cosecant is 1 over the sine, right? Minus the sine of x. Okay, so this is a good start. Now I want common denominators, just like we did earlier in the video here, which means if I multiply this part here by sine of x over sine of x, which will give me sine squared of x over sine of x. I'll have common denominators, and then I can combine these two things together. So now I got 1 minus sine squared of x in the numerator over sine of x, okay? Now, my Pythagorean identity is, remember that sine squared plus cosine squared equals 1. So if I manipulated that, and I subtracted sine squared from both sides, that would give me cosine squared of x over sine squared of x, okay? Which is actually the same thing as, oops, I should change colors here. Remember how I manipulated that cosine So these two are the same thing, okay? Which means I'm done at that point. I've proven it, okay? So I know I manipulated the right side a little bit just to make it look like I could make it easier to get there. But I didn't do anything to both sides of the equation, which is really the thing that some students try to do. All right, so next one. Okay, this one. So clearly I'm going to work with the left side. Don't take the right side and try to make it into the left side. It'll be a headache. The left side, this one looks hard, but it really comes together nicely. Remember, sine squared plus cosine squared, that's one of the biggies you really got to know. That's 1. And then denominator, I've got cosine squared of x. Secant is 1 over the cosine. So therefore, secant squared is 1 over cosine squared, which means that's 1 when you multiply them together, right? Anything times its inverse is 1. So I'm done, all right? I got to there. That one actually came together real nice, all right? So sometimes even though they look crazy hard, they're not, okay? So that's 1 times 1 over 1, 1, 1, 1, 1, a lot of ones. All right, number 8. So I'm definitely taking that left side. That looks harder to me, okay? There's more stuff there. And it's also multiplication. Multiplying that together, it shouldn't be too hard. So let's change secant squared here, because I don't think I like the secant squared so much. Okay, so if I go back to my identities, I find this one, all right? Which means that if I subtracted 1 from both sides there, I would get that secant squared minus 1 equals tangent squared. So I'm going to change that to tangent squared. So that's tangent squared of x times sine squared of x minus 1. All right, good. Now, tangent squared, that's the same. Tangent is equal to sine over cosine, right? Which means that this is the same as sine squared of x over cosine squared of x times sine squared of x minus 1. Now I'm looking at the sine squared of x minus 1, and remember, there's an identity for that one too. That sine squared plus cosine squared of x equals 1, which means if I manipulate that equation and subtract 1 from both sides and then subtract cosine squared from both sides, I get sine squared of x minus 1 equals negative cosine squared of x. So that's what I got here. This turns into negative cosine squared of x. Which means I get some stuff to cancel out, which is my goal, right? I want to turn things into cosines, or into sines rather, which means that this cancels with this. This is like negative 1 though, I can't lose that. So I got negative 1 times sine squared of x, which I think is actually my goal, right? There it is. It's just the only thing is it doesn't have the 1 on front, which is implied. And there we go, I got it. So I'm done manipulating now. Number 9, looking at this one here. Okay. I'm going to manipulate the left side. Okay, now if I look at the right side, I see only cosines over there. So I'm thinking maybe if I change that sine squared into cosines, that would be a good start. So once again, I'm going back to that same Pythagorean identity. Sine squared plus cosine squared equals 1, which means if I get the sine squared alone, what I got is 1 minus cosine squared. So I can change that to 1 minus cosine squared of x. Okay, so that's what that equals. So now I'm here. Now I'm going to distribute that subtraction sign there. Okay, so I get minus 1 and then plus cosine squared of x. So I just distributed this to both. Change both the signs. And now, look, I got cosine squared of x plus cosine squared of x. That's y plus y is 2y. Therefore, this is 2 times cosine squared of x minus 1. And I'm done now, right? Because now I got that was my goal, is to get it to be that. Okay, so that one's done. Next one. So This one, which side are you going to tackle? Okay, so this one, the right side, I am changed cosecant to 1 over sine, and I changed the secant to 1 over cosine. You know, usually that's kind of how I go. I try to change things to sines and cosines whenever possible. All right, and then this one, so cosecant squared, that would be the same as 1 over sine squared. Okay, so I'm going to do these as two separate fractions. I'll get to the cotangent in a minute. So this is 1 over sine squared theta. And then the cotangent, this is 1 over tangent. So since I got this in the denominator, I'm going to flip it, okay? So that's going to be regular tangent. Now, I can change tangent, right? Tangent's sine over cosine. So now I'm, excuse me, now I'm here. Now I've got two signs in the denominator and I got one sign in the numerator, which means that I can cancel some of those out, right? This cancels out with that, which means I'm left with 1 over sine of theta times 1 over cosine of theta. And that was my goal, right? So that one's actually all done now. So I am good over there like that. One way to do these, you know, and here's another way I could have done the same problem. Perhaps you looked at that numerator and said, geez, I'm going to take the left side and manipulate that, and I see that cosecant squared is equal to 1 plus cotangent squared. That's one of my things on my formula sheet. So if I change that to 1 plus cotangent squared of theta over cotangent of theta, and now I've got two things in the numerator over the same denominator, which means I can split them up, right? 1 over cotangent of theta plus cotangent squared of theta over cotangent of theta. Start manipulating this. So cotangent, that's the same as 1 over the cotangent, sine over cosine, right? Cosine over sine would be cotangent. So this is the same. I got to do some quick multiplying over here. So this is the same as 1 over, cotangent is cosine over sine. So I'm going to flip and multiply quickly, which this one's going to give me sine over cosine. This one, I got cosine squared of theta. If I flip that other one upside down, I get sine over cosine. And then I can cancel out some cosines here. That squared cancels with that. I made a mistake there. If we could back up just for a second. I changed that cotangent to a cosine for some reason. Just a human error. Please fix that. So I changed it to red there. So it should be cotangent over cotangent squared over cotangent, which is good old regular cotangent. So I'm going to change this. So cotangent squared divided by cotangent is a regular cotangent. Cotangent is cosine over sine. Okay, now I can multiply by the other denominator to make common denominators. When I do that, I get sine squared of theta plus cosine squared of theta over cosine theta sine of theta. And remember that sine squared plus cosine squared is 1, which gives me 1 over cosine of theta sine of theta, which is what my goal was. Okay, I had them in separate fractions, but it's the same thing. So that's it. I'm done with that one. Sorry for any mistake there. And that's all I got for today. So have a great night, and I'll see you all soon.